Check it out now, y'all.
nanoHUB-U Online Instruction.
Welcome back. Today I'm gonna talk about homework 1, the solution. I'm gonna go over the highlights. What we discussed during week 1 were concepts like voltage, charge, energy density, power. Okay, and we talked about some of the lingo as well. And the homework tries to put all these concepts together to try to read the information from a battery manufacturer, specifically to basically pick a set of materials, okay, and the 5 problems that you got, play over the different aspects associated with them, okay. In this case, it was specified that the thickness of the layer, okay, the thickness of the electrode was going to be 100 micrometers for all of them. And it was also specified that the porosity for those systems where it was relevant, okay, was going to be 35%. Okay, there were 2 types of problems here. Okay, one of them correspond about porous structures, and others were structures were actually dense, thin films, just to show you what is the effect of porosity on the energy density of the system. Okay, and from those 2 types of problems, half of those problems used a graphite anode, and the other half used a pure lithium anode. The reason for this is just to show you how the energy density of the cell is being determined by how you specify the both cathode and anode layers. Okay, if we go there to the plot, this is a sketch of the plot that we used in the homework. Graphite gives you a potential, you can see over here, of about 250 millivolts. Okay, while the lithium metal anode will give you effectively a potential of 0 volts. Okay, why? Because the voltage that we're measuring is with respect to the lithium metal. Okay, so in any case, all the cathode materials of the homework, there you can see them, they're all in this window, which makes them actually give an energy density that is going to be always greater, the charge density, okay, in milliamps hour per kilogram. Actually, it's an amps hour per kilogram. Okay, the energy density is always going to be, the charge that material is going to give you is always going to be less than graphite. You can see it's always here in the 400s. Okay, so it doesn't matter what you do, the limiting rate is going to be the cathode. Okay, so for all these problems, and I should say it here in general, for all these problems, one of the things you have to acknowledge is that the limiting rate, or if you prefer, what determines the energy density is the cathode layer. Okay, so again, you can see everything's here is on the hundreds to 300s range. Okay, you can see it there, while graphite is here on the 400s, and lithium metal is over there in the 4000s. Okay, now going to our first system. Okay, so for this system, we have the lithium metal for question 1. We have a lithium metal anode sandwiched with a lithium cobalt oxide electrode. Okay, we can read that here from the plot. You can see here that the voltage is around 4 volts, and from the plot, and in this case, you can read it directly from your specific plot that you have. Okay, it's the charge should be around 150 and maybe 110. Okay, as you read it there, and what you want is, in this case, be able to specify what is the energy density of the system. If you remember from the notes of the class, right, the energy is going to be effectively the potential that this battery gives us. right? The equilibrium potential, in this case, times the charge. Okay, because we want to include the porosity of the system, we need to subtract, okay, the porous, the porosity that we have to put in it, and of course the electrode thickness, okay, which we have also over there. So you can see really actually extracting the energy density of the system really boils down really to just reading the plot and specify that number, okay? In this case, this voltage phi really corresponds to the number as we read it over here, okay? And the charge corresponds to its corresponding charge as we get it, okay? And this one will have, of course, units of joules per kilogram, okay? Or you can also rewrite this in watt-hours per kilogram, okay? And for this particular problem, okay, the answer is answer B, okay, which is 453 joules per kilogram, okay? We can do the exact same problem, we can repeat the exact same problem. I'm going to erase the answer here for question 2. Okay, very simple question. In that case, the problems are very similar. For question 2, where we have graphite, which is LiXC6, where the cathode in this case is iron phosphate. Okay, iron phosphate as compared to lithium cobalt oxide, you can see in this plot, seems to have comparable energy density as compared to the lithium cobalt oxide, but the voltage of lithium iron phosphate, it has different ranges, so if we want to estimate it, I would take actually the lower bound. Okay, so really you can see you lose an entire bolt from using lithium iron phosphate as compared to lithium cobalt oxide, and typically this is why these chemistries are referred to as high energy density. And these over here are used typically for high power density. Okay, and well, as we read the voltage, well, I have to write against the energy. The energy in this case will be the voltage as I read it from the plot. I will specify a 3. Okay, but in this case, I have to subtract the voltage associated to graphite. So the actual voltage for lithium iron phosphate battery will be this distance, okay, as compared to before where I was actually able to use the whole 4 volts. So I have to subtract this 250 millivolts. So in this case, the voltage will be the voltage of the cathode minus the voltage of the anode. And here's where you have your 250 millivolts. Okay, the charge is still the charge of the cathode. Okay, that's as I read it from the plot. Okay, the same thickness and the same porosity, and that specifies the energy density. Okay, in this case, for question number 2, the answer is C, which is 311.8 joules per kilogram. And you can see how you actually lose some energy by subtracting the voltage and having to pick a different value for the charge. Okay, now that's question number 2. Question number 3 is very similar to question number 2, except that instead of using lithium iron phosphate, we're using lithium manganese oxide. So you can see how we are roughly in the same window. So I guess I would use somewhere between 2 and 3 just to specify that. You can either take it as a lower bound or an upper bound and still have that type of response. Okay. For the next question, oh, and I forgot to say, for question number 3, the answer is D. Okay. Now, for question number 4, in this case, we have a graphite. Lithium cobalt oxide thin film. And this is a thin film. What distinguishes this from the previous problem, okay, there are several differences. One of them is the fact that I have to subtract the voltage associated to the graphite layer. Okay, it's still the same charge as I read it for lithium cobalt oxide. Okay, however, oh, and I have to specify the thickness of the film as still the same thickness, but because the cathode is a thin film, I don't have to subtract. Before I used to have this term. Okay, now I can actually ignore that term because it's a dense thin film, and I don't have to basically take out this 35% of the material that you will get from in the previous case. So for question number 4, the answer is A, 607.5 joules per kilogram, which if you compare it to the first question, which is 453.6 joules per kilogram, you actually get more energy density if you put it in thin film form, because you actually do not include the porosity contribution, even though you're using actually a material that gives you a voltage drop, which is graphite. And the reason is because in this case you can see how the porosity plays a very important role at controlling the energy density. And of course, as we have been discussing, that porosity is necessary because without it, we will not be able to access that material in the back. So a thin film may give you a high energy density, but will give you a very low power density because you have very small area, very large diffusion distances to be able to access that material. Okay, so that's question number 4. And let's see, question number 5 is very similar to question number 2. I'm gonna put it here. For question number 5, we have now a lithium metal. Okay, and in this case we have a lithium iron phosphate. Okay, and this one is also a thin film. So the energy you can see is very similar. You have the voltage of the cathode minus the voltage of the anode times the charge that the cathode provides times the thickness, the same thickness, no porosity, again because it's a thin film. Okay, notice that in this case, because we're using a lithium anode, we don't have to subtract the 250 millivolts. However, notice that this one, lithium cobalt oxide, essentially gives us 4 volts, what lithium iron phosphate gives us around 3 volts. So we lose a whole volt as a result of that. And because of that, this one gives us an energy density of 486 joules per kilogram, or if you prefer, answer E. Okay, so this electrode gives us less energy density as compared to the graphite-based thin film electrode. Why? Because it doesn't matter what we do. The voltage is the one that is controlling the response of the cell. Okay, and the aim over all of the homework was to make you think of these concepts on what parameter is the one that's controlling the most response. Notice that for all of them, you have to admit that the limiting rate is determined by the cathode. Okay, and you have to distinguish when to use a porous structure. And well, in this case, the thickness was left fixed simply so that we have a common baseline to make these comparisons. Okay, and I'm hoping that you have also learned that different chemistries will give you different types of response, and you should pick them not only based on the capacity, but also based on if you want a high energy density application or a high power density application. Okay, thank you.